Turning to slide 4, I want to give a background for multi-step modeling and introduce the concepts of the measurement model versus the full model. So top left here we have 6 latent class indicators of a latent class variable C, and that is our measurement instrument, those 6 indicators. In our analysis here with simulated data, they're going to be binary. And the full model is the model that we're really interested in ultimately, and it adds to those 6 indicators a further variable, it could be several variables, in this case designated by y. So y is considered a distal outcome. It's a variable that's predicted by the latent class variable. In the measurement model analysis, you determine the latent classes, you determine how many they are, and you interpret them. One example is latent class analysis. There could be other measurement models as well. In the full model, you add other variables to the measurement model, and we have then the example on the right here of distal outcome predicted by the latent class variable. Now you may want to ask yourself, that distal outcome looks like just another indicator of latent class variable C, in addition to the 6 that we have here. And that is the problem, because we really want to consider these 6 variables as our measurement instrument that captures what C is, and then we want to predict Y from that C. And to be able to do that, we need multi-step modeling. So in slide 5 then, I give the multi-step rationale, claiming that there is a need to separate the estimation of the measurement model from the full model so the latent classes don't change from one step to the other, from the measurement model to the full model. Because that, for instance, that distal outcome in the full model may change the latent class formation. And that would be undesirable. For instance, if the full model outcome is measured, the distal outcome is measured at a later time point than the variables of the measurement model. Take, for instance, measures of aggressive disruptive behavior in the classroom in elementary school, and the distal outcome that is juvenile delinquency later on in life. And where you want to predict from the measures that you have in elementary school, you don't yet have the distal outcome Y. And you want to see how well you can predict from the early time point to a later time point. Covariates in the full model may also affect the latent class formation and the determination of the number of classes. And it's inconvenient to have them influence the latent classes. When you want to experiment with different sets of covariates, you would have to do the latent class enumeration over again. So the separation of these 2 estimation steps is done by the multi-step approaches that I'm going to present. So the first step again is the latent classes being determined only by the measurement model, and the last step adding the distal outcomes and or covariates of the full model. And how we do that exactly statistically is shown in the statistical methodology section, and what I will try to do is to show it to you in a more intuitive fashion with as few technicalities as possible. So slide 6 then, we talk about the multi-step approaches of 3-step BCH and 2-step in a first intuitive fashion. Now, the 3-step and the BCH approaches use the so-called posterior probabilities from the estimated measurement model to determine each individual's most likely class membership and take its measurement area into account. And in the next couple of slides, I'm going to show you what the posterior probability actually is. So in 3-step, that measurement error is handled by the last step fixing a logits of the measurement model So those are the logits in the relationship between the latent class indicators regressed on the latent class variable. And that's done by taking measurement error into account in the most likely class classification that I will describe in a couple of slides forward. In the BCH approach, the last step instead uses weights from the measurement model to take measurement error into account in this most likely class classification. Two-step, the third approach, takes a totally different tack. It uses fixed measurement model parameters in the last step, fixing the measurement model from the first step and thereby avoiding measurement error and keep the classes the same between the two steps. Slide 7, then we take a closer look at what a posterior probability is and how it relates to most likely class, or MLC. So a posterior probability is a probability of an individual being in each class based on the estimated model and the individual's data. So the estimated model uses all individuals' data. And now we go and ask, what's the posterior probability for an individual? And that depends not only on the estimated model, but this individual's data. And in Mplus, these posterior probabilities for each individual and each class are saved together with the most likely class, MLC, using the C probabilities option of the save data command. So for instance, this is an example that we're going to see several times. 6 individuals, 3 latent classes. So you have the individuals here, individual 1 through 6, as rows, and the columns are probability of being class 1, probability of being class 2, probability of being in class 3, and with most likely class designation. So for instance, for the first individual, the probability that he or she is in class 1 is 0.5 and 0.3 versus 0.2 in the next two classes. So the most likely class is class number 1, which is the highest one. For individual 2, you have a very high probability of being in class 3, and the class probabilities for the other classes are lower. Here MLC is 3, and so on. So for each of these rows, the probabilities sum to 1. 0.5 plus 0.3 plus 0.2 is 1. And for each column, the average C probability gives the class probability. So you average over these values and you get 0.30. On slide 8, let's take a closer look at the measurement error in this MLC, most likely class variable. And I claim here that from the table of posterior probabilities for all individuals, it is possible to compute a summary table of classification quality. We're going to show this summary table for the example of the 6 individuals on the previous slide. But in real data, you will get it for your whole sample, of course, for the whole sample of people in your data. Now, what we're looking at here is a table where the rows correspond to the latent classes of the latent class variable C, and the corresponding columns for the observed most likely class variable. So both of these variables are nominal variables, that is, unordered categorical variables. But here, C, representing the rows, correspond to the true status of a person, and the columns correspond to the observed counterpart, which may be measured with error. So let's take a look at an individual whose true class membership is 1. The probability then for the most likely class variable being observed as 1 is 0.56. It is not 1.0 as we would want it to be. It's not perfect correspondence between the two variables. We have measurement error in the sense that you could be misclassified as a category 2 person by 0.38 probability, and it's a category 3 person by probability 0.06. So just repeating then that MLC is a perfect measure of C if all diagonal elements are 1 and all off-diagonal elements 0, and non-zero off-diagonal elements correspond to MLC measurement error. Now the 3-step and BCH multi-step approaches take this measurement error into account in their last step analysis. And we actually work through this example of the hypothetical 6 individuals in the statistical methodology section in detail. It's not complicated, it's just cumbersome. What you will see in the Mplus output is this table here, which comes out as in the middle of a sequence of 3 tables, which we'll refer to as we get into a data analysis. Now, in Mplus, we have both automatic and manual multi-step approaches. And the automatic multi-step approaches are only available for certain settings, which simplify the analysis. But in general, you typically need manual approaches that have much more general scope. So you have the automatic column, the manual column, distal outcomes versus covariates. So for distal outcomes, we have the 3-step and BCH methods, whereas the manual approach can add 2-step. For covariates, we have only 3-step. It's called R 3-step, regression 3-step, regressing on X's, whereas the manual approach then adds BCH and 2-step. So following then, I'm going to discuss these 2 possibilities of automatic and manual, and begin with the common starting point of the measurement model, the first step of the analysis.